Yep, let's wait for one more minute and then we'll get started. All right. Okay, why don't we get started now? And then maybe the rest they can join later in the meeting as well. Okay, let me share my screen. So right now we'll be doing X verification. So let's see. All right, so the topic for right now is X verification. We'll see how we deal with X propagation throughout the simulation flow. So on this topic, there's a few problem causing X propagation and what does it actually cause. So the problem is it is coming from the sources of X. And then we have also either optimism or pessimism in terms of treating X, and also the simulation and synthesis mismatch. So simulation treats X and synthesis treats X in a different way. So we'll be checking that out later in the slide as well. So sources of X, how many sources of X that can actually comes in simulation? So there are actually three sources of X being generated in simulation. So the first one is assigned X value. So let's say you assign it in a parameter or you assign it in test bench to X, and then you want to have a reset on that floor. But this assigned by designers is under the condition where which it should not occur, or it comes from a default case statement. The second sources of X, it can also come from initialized state elements. So if you did not initialize any registers or any elements during your simulation, that reg will be X, or if you did not use any init reg 0 or init reg sv seed random, so it will be x at the start, and then it only propagates to the proper value at certain time of point. So you also have incomplete reset operation, which causes the state to turn to X at the start. And there's also X coming from power aware simulation, where we seen just now there data corruption will cause the data to be propagated to X. And on secondary sources, it can be also a bus conflict, or there is also a multiple driver driving a signal. Then it does not know which signal to take in at the certain period of time. Or it can be also out of range index, and it can be also incorrect arithmetic, where it would divide something by 0, then the simulator does not know how to treat this value. So what are the challenges when we deal with this X propagation? So the problem is silicon value resolved to only 1 and 0. So in silicon world, there is no value of X. But in simulator, we will have this value of X when we have a non-deterministic value. So this causes a problem between simulation and silicon mismatch. Simulation X is a logic value where it is distinguishable from 0, 1, or high Z. But however, in hardware, X is treated as a don't care, which may resolve to 0 or 1. And simulation results might be more perministic or more optimistic, depends on how do you want the simulator to treat it. So in this term, let me explain more. So optimistic means that the simulator will try to resolve this X to either 0 or 1, but pessimistic, they will always stay at X throughout the propagation of your simulation. So again, let me go into detail. So X-permeism is a definition by propagation of X in simulation which don't pose a problem in silicon, but it may lead to unnecessary debug, and it makes reset logic appear incomplete. But for X optimism, we try to resolve this X to either 0 or 1 in simulation, makes an unknown value appears as a known value. So your X might be end up settled down or resolved to 1 or 0. So in this case, we can miss the problem which might only surface in silicon. And we require advanced debugging to determine the source of X here, because we already resolved at some point of time in simulation. So we don't really know where this X is coming from. So more on the difference between X-permeism and X-optimism. So X-permeism, just to as a refresher, it makes known value appear as unknown. And X-optimism makes an unknown value appears as a known value. So in terms of X-permeism, it can be termed as false X, because this X will propagate throughout the simulation and it does not resolve it by itself. And for X optimism, this can be termed as real X, because this X is resolved to some value, but we don't really know what is the real value is. The propagation of X in simulation which don't pose a problem in silicon, and X optimism is blocking a propagation of such X in simulation might hide a bug later on in the silicon. So X-permeism mainly occurs in gate level simulation, while X-optimism mainly occurs in RTL simulation. So we take this for example. This is a loop where A equals to unknown, and then it will feedback to, it will goes to this NOT gate and then go to the AND gate. In simulation, B is unknown, but in hardware, B equals to 0. And if you like to guess why is it 0, it's because of this combinational logic. So if X is either 1 or 0, so X will be propagated to one of the AND gate, and the other one will be a NOT gate. So both of these will be 0 at certain point. Both of these, either one of these will be at 0 at certain point. So since this is a NOT gate, so hardware will treat it as a 0 by default. But in terms of simulator, in simulator for mux, we get X if its selector equals to X. But for hardware, since both of these are 1, whatever the selector comes value, it will take 1. And we will look at this in detail later on in the later slide. So what are the further issues with X handling? So we can see there's a mismatch between synthesis and simulation. So it's a very clear message that we have inconsistent simulation and synthesis schematics. In synthesis, X is a don't care, and it will be changed freely to either 0 or 1. In simulation, X is a logic value distinct from 0, 1, or Z. So let's take, for example, this line of code. We have a always block with a select A and B. So the select here is used in a if-else statement. If select Q, you get A. Else Q, you get B. So in this line of code, we can actually resolve this into 3 different combinational logic. And these 3 different combinational logics have their own synthesis truth table. So the first synthesis truth table, when select is X, A, B, and AB is 0, and Q will be also 0 because of the combinational block here. But in terms of the rest, if select is X, Q will be unknown as well. But let's see from simulation truth table. When select is X, all of it will be, if it's X optimism, all of it will be resolved to one of the value. And the second problem with issues at handling X handling is that simulation results may not match the results in silicon. So X optimism makes unknown value appear as unknown, and X optimism makes unknown value appears as known. And in terms of simulation, can miss X related problems in hardware. If it's X optimism, it makes the test pass in simulation, but we might not know if there's any bug hidden in this code. So on silicon truth table, we can either resolve it to 0 or 1, no matter if it's X on select, but X optimism will resolve it to 1 or 0 based on the combo logic. We cannot have 2 different values on the output queue. And simulation can expose that problems that doesn't exist in hardware. So we have a lot of X, and there might be a lot of problems that might not exist in hardware, because in hardware, we don't really take X in consideration, and it will eventually settles to 1 or 0, but that might cause an issue in simulation side. So therefore, unnecessary reset logic may be added to silicon from your simulation, just to make your simulation pass. And now we look at some scenario of X optimism. This is a conditional statement where common X issue in simulation. So this is if statement. So if condition, so if condition equals to X, your range A, if condition equals to 1, your range A, you get assigned the value of F0, else you get assigned value of range A. Because this is in simulation, as long as the condition is not equal to 1, it will go into the else statement. So simulation will pick this. In terms of case statement, case condition is if it's X. Well, let's see what's the case. If it's 2-bit 0 on condition, reg B will get F0. and 2-bit 1 will get reg f1. On default, it will get reg f2. Since this does not match any of the condition given here, so it will go to the default value and it will be assigned to f2. But this is different in terms of hardware. Hardware will consider all scenarios. Simulation is not simulating, at least in this specific condition, what happens in the actual hardware. So some bugs cannot be detected using simulation alone. So let's see another example on X optimism. So this is for age triggering. So it appears commonly in a situation where the clocking logic always at pause age clock, and then Q will be assigned to A. What happens if the pause age clock change from 0 to X? Is this still considered as a pause age? In simulation world, simulations still execute this as 0 to X is still considered as a pause age. So Q will be assigned to a value A. And again, this is different in hardware behavior. So we prove again some bugs cannot be detected using simulation, especially for resistors without a reset. So this is a UDP table. So to those who have experience in gate level simulation, so this is the UDP table. So UDP table, we can handle X definition for X age behavior better because in UDP table, we will have all the conditions out for the clock. So for example, if clock goes from 0 to 1, 0 to 1, 0 to X, or unknown to 0, or it's totally unknown, then it will show you, then you can define what happens to the output Q from the input D. Now let's go into X pessimism. So X pessimism is, it might cause unnecessary debugging because X pessimism produces the worst case for X handling in, at least in simulation world. So X pessimism will propagate X throughout the simulation, no matter what kind of logic it goes through. It doesn't resolve in any of the logic. So X pessimism appears commonly in simulation where it have arithmetic operators, reconvergent fan out, potential reset issue. So let's say our example 1 here. So let's say we assign B equals to A and not of A. So the combo logic will be appear as like this. So simulation, if B equals to X, if A equals to X, your input equals to X, simulation for X pessimism will get X as well. But as we can see from the previous case, since this is a and a not A, anyhow, the AND gate will get either one of the value of 0. So the end result will be 0. And in example 2, we assign a marks to select A and B and not of select A and B. So if select is X, simulation will also take this as X, but hardware will take it as 1. So on X pessimism sequential reconvergence, so positive and negative value may reconverge several cycles later in hardware. So if the X is value X initially, it will eventually settle down to a constant in hardware. But in simulation, it might be more difficult to detect and eliminate in this situation. How about gate level then? Let's see for gate level. So pessimism introduced by reconvergence logic path generated by synthesis. There's a redundant logic with constant value. So we will have different results from functional models versus UDP models because UDP's models acts more accurately as we will include what kind of output we want when we have X. Also, there would be uninitialized registers at gate level. So registers are missing reset or incomplete reset sequence here. Let's look more details in terms of RTL versus gate level. So on RTL, we mainly see issues with X optimism due to Verilog LRM behavior. But GLS will see mainly issues with X pessimism. There is a very rare case of X pessimism in RTL because we tried to resolve it in RTL. And for GLS, there is no occurrence of X optimism as Verilog schematics are translated into gate modeling. In RTL, it's important to debug and fix this X optimism issue early in the design cycle so that it doesn't cause it as a bug in silicon. For gate level, it's important to identify which is the fault X and fix them quickly. Because in simulation, there's a lot of issue with false X, and in order for us to refocus it on the real X. So the value of X initially, it will settle down to a constant later in hardware, as we've seen earlier. So this pessimism is introduced by reconvergence of logic path generated by synthesis. And the redundant logic with constant value, uninitialized registers, different results from function models versus UDPs. So now we know all of the causes and what it will happen if we have X propagated. But how do we mitigate this issue? So on Questa side, mitigating X optimism, we use strict coding guidelines so that it makes the code harder to read and 100% enforcement is difficult. So we can also change the simulation schematics, but it's very disruptive change. The X in simulation can be helpful to detect some errors. And to mitigate expertism, we randomly initialize uninitialized registers to 0 or 1. But this will cause simulation many times to catch the problem. And we can add extra reset logic to make sure that the design is really reset, but it costs extra power and die area. So on Questa X prop solution, we have total of 3 solutions to resolve this. So one of the solution is to determine the sources of propagated X would require more time to debug later in the verification cycle. So engineers will need to spend more time to identify sources of X and then analyze and redesign the reset logic, spend more time testing the initialization of the design, and create explicit checks to report X. We can also have dynamic solution where Cresta XProp solution consists of mechanism to handle the propagation of X. So this is to ensure the simulation closely matches the silicon behavior and traps the source of X during simulation and ensure the signal resolve to a known value if possible. Or we can also use formal solution where Cresta X check app automatically generates and analyzes assertions to rapidly identify X state issues. It will exhaustively identify all X state issues, enable exhaustive evaluation of circuit startup and post-reset X issue, and integrate with the Questa SIM with complementary X-prop analysis. So there's another Questa X check app we can make use of, but this is a topic for another day. So we'll take a look at this instead. Questa X prop modes. So using X prop simulation flow, we can have 3 different modes. So one is the track mode, then resolve mode, and the pass mode. So for X prop track mode, we report an error message the instant an X is detected in the simulation. So we trap the X at the very earliest stage. So this will mitigate the X optimism issue. It doesn't resolve the X by itself, so we know where the X comes from. So this doesn't alter the simulation. But in resolve mode, X is handled as a don't care when a known value can be determined. So X will be automatically resolved by the simulation itself. This will mitigate X optimism and X optimism issue, but this will alter the simulation. So your end result might be different than any other mode. For pass mode, X is propagated even when a known value could be determined. So this is the most pessimistic approach where the X will be propagated throughout the simulation even though a known value can be determined. So this will also alter the simulation result. So in conclusion, X state trapping assertions immediate assertion and trap the occurrence of X. And for visualizer debug, we can see the message from message viewer, assertion viewer, or driver tracing. We'll now go into looking at these different modes. So X propagation for resolve mode. So if I wanted to clarify again, resolve mode is to resolve X to a known value if possible. So resolve mode with a conditional statement. So let's say we take this again, this small code for to destruct this small code. So if condition equals to 1, then reg A will get F0, else reg A will get F1. So we can see that the condition is X. And then we have a different truth table for F1 and F2. And RTL simulation, the normal RTL simulation will resolve it by itself. So it's 0 here, and 1 here, and 0 here, and 1. But in resolve state, when F is equals to F1, the value of condition is don't care. So it's similar to silicon where X is masked. In terms of X trapping implicit assertion, so we have conditional statement, always com block, where we have the same code as previous slide. And conditional statement with implicit assertion will be included. So at this always com block, at this stage, assertion is already asserted. So this is to catch the X in conditional expression as soon as possible. So the simulation will report an error here directly, and you can fix your X very early in the stage here. On X propagation for pass mode, so it's implemented for the worst case scenario where if there's X in any of the signal or reset or set, then it will propagate X throughout the simulation. So this is for pass mode, and then let me go back to resolve mode. It will only resolve if we can confidently say if it's F0 equals to F1, then X is don't care. Then we'll get the value of F0 of F1. So if F0 of F1 is 1, so both of them are 1 and then X will be don't care, then we'll get the value of 1. This is resolve mode. It will resolve as logically as possible. But X in this case is still propagated as we cannot determine the true value of reg A here when condition is X. So we have also X propagation for edge trigger. So in this tree mode, edge trigger will be, the simulation for output will be different. So let's say we take this example again for, for X trigger. So if clock changes from 0 to X, so this will have a edge triggering in simulation. So when A equals to 0, on resolve mode, this will be 0. And for pass mode, it will pass the value of X. Since A and the previous value of Q is 0, that's why the resolve mode is 0. It's the same situation as previous, where resolve mode, when the new output and the previous output is the same, then it will confidently put the value in. For the value that we cannot determine whether it's 1 or 0, resolve mode will treat it as X. So I've shared how do all these modes comes in handy, but how do we really invoke it in QuestaSim? So to invoke it, and the usage of xprop is by using dash xprop in VOP, so the optimization phase. And then you can bracket and common mode equals to what type of mode do you want. So it's either you want it to be resolve mode, or do you want it to be a pass mode, or do you want it to be a trap mode. And then you can have the report it out and the severity, whether you want it to be in an error or a warning. So mode can be set to trap, resolve, or pass, as I mentioned just now. Or if you didn't set this mode, the default is to resolve. Reporting options specify the severity of the messages and assertions. So it can be set to fatal, error, warning, info, or you can be suppressed. And the object options specify the scopes. So it's either the instance or design unit name. So you can specify where do you want this X propagation to be. If you don't want it to be a top-down X propagation, you can also specify the path to it. And there's a precedent order of X propagation arguments. So meaning if you put instance in front of your object here, and then you have another instance, then the X propagation will only do for the first instance first and then the second instance. So VOP command follows the precedent rules, where the last specified xprop argument takes precedent over any of the previous xprop options. So for example, let's take this example here. So xprop mode equals to resolve, and then there's also xprop mode equals to none. So you have these two different options in the same VOP line, but the xprop mode none is the latest option that you put in. So this will take precedent over this first. So xprop is disabled in this case, where this xprop none is at your last of the command. And for example 2, so xprop is first disabled to mode none for all instance under top child, and then the second instance xprop argument explicitly enable xprop for the subchild instance. So why do we want this kind of behavior? It's because you want to make sure that the xprop mode is not active in all of the instance under child, but it's only active for this top child and subchild. And xprop messages in transcript. So messages indicate the lines numbers of HDL file associated, and it may include a unique number to identify each variable which is affected by X propagation within the block. So a few messages you might see in message view is this xprop underscore com. So this is inside the conditional always logic. Or if it's FF, it is inside sequential always block. Or your X could be coming from a clock signal as well, or inferred latch, or even inferred FSM variable. Let's see this transcript for example. So we have a xprop com, which is saying that there's a x inside conditional logic that select goes to x. And then there's another warning where xprop ff, it's inside sequential logic, a reset goes to x. Xprep can be enabled or disabled using vsim command line as we seen just now. So users can also control the assertion message being reported. If you use this line xprop assert limit, then you can assert on how many messages do you want it to assert. So default n equals to 5, you can set n minus 1 for unlimited assertion messages. So this is the example command. So, so for example, you want to control when to switch on the xprop and when to switch off and on the xprop. Usually in this scenario, people would like to switch off xprop at time 0, and then you run the simulation for a certain simulation time, and then only you enable the xprop. So why do people do this? So the answer is simple. People do this is because they would like their resistors to be initialized first, and the reset has gone through properly throughout the simulation before you use xprop. So if you have any uninitialized registers at time 0, it will propagate the x. So we do not want any additional propagation of x. So if your design have any resets at certain time, so you have to reset it and then only you enable xprop. So what's the use model? So you can disable xprop on test bench hierarchy and only enable on synthesizable DUT. Because in test bench, there might be a lot of users of X, but in synthesizable DUT, you don't really expect X to be in this synthesizable DUT. And then you, again, like I mentioned, you enable xprop after the reset operation and the initialization have complete. So you don't propagate unnecessary X. So users can also specify which xprop checks can be disabled using the assertion enable command. So you can filter out what kind of xprop checks that you don't want to see first by using assertion enable dash off dash filter xprop, let's say for example xprop com for the line number or the instance or path name. So this will override the export enable command and disable reporting the specified group of messages. And the dash filter option selects only those assertions which matches the specific patterns. So for example, if you filter out xprop combo, you will get only this kind of messages. So this will recursively disable all xprop messages which are found in conditional blocks under TB T1. So what's our advice for best practices on running xprop? So in simulation, the design nets and reg usually remains X during reset phase. So until the initialization sequence is complete. So hence, it is not recommended to turn on xprop in reset phase. We will suggest to turn off this xprop during reset phase and wait for the reset phase to finish, and then enable xprop through the following tickle commands at vsim. So you can use this do command, disable xprop, and then run certain time of period, and then you enable the xprop here. So remember, the sources of X propagation might be coming from uninitialized flops. Hence, after the reset sequence is over, we can rule out these uninitialized flops and debug the first triggered assertion. We would also like to recommend cleaning these uninitialized flops in 2 or 3 iterations. So this will clean up most of the RTL codes. And because of the first X, which would result in X propagation, So fixing the first sources would eventually fix 95% of the X propagation in RTL. So in most cases, you'll fix 100% of it. Hence, the best practice to achieve the best result is to run X prop in trap mode. Although this will require a lot of manual effort from the engineers, but trap mode will trigger the assertion immediately, and it will ensure there's no propagation of X and it doesn't alter the simulation behavior. Then you can, if you are very concerned on the X issue, then you can directly debug the X issue here. Then after cleaning those first sources of trap mode assertions, then you run xprop to resolve mode. And required, you can finally run xprop in pass mode. Let's see how is it in our use model. So xprop in trap mode / resolve mode, and then we can see the vopt command below here. Let's jump into this vopt command. So vopt, your top module, so meaning the TB, and we don't use plus ACC anymore, we use -debug. And then we have xprop at comma mode equals to resolve, and then we want the X to be reported as an error severity. So comma report equals to error. So we output the optimized design unit, and then we add also -debug here. So since we have a -debug here, we don't need plus ACC, but we'll need -access so that they can access the cell as well if you need it. And then we have plus design file to generate the database for visualizer. Then we have to ensure xprop is initialized after reset. So let's see this do file here. So this do file is doing do xprop.do. So this xprop.do will have xprop assert limit of 1. So there's only one message limit per time. And we disable xprop at time 0. So after the reset phase, which in this case runs 6 nanoseconds, we enable again the xprop, and then we run the whole simulation. So this will remove unnecessary noises that show at time 0 because of the uninitialized registers. And we can limit our assertion to represent only one so that we can fix one at a time. So all the assertions and errors appears after reset most probably are genuine error, then you might have to fix that. Okay. Then there's also a short video on how do you enable this. Let's try to watch this one. It's a very short video on how to enable xprop in Questa. I don't think there's a sound, so we'll just have to follow through. Let me see if the video is out of scale. Let me check. Should be okay, I guess. So this is using xprop mode in vopt command, and they are using resolve xprop mode and report error. So you make run all, make all. And we can see the xprop error message being reported for X propagation. So now they are doing invoking the visualizer. Let's see it also. So then we navigate to the message viewer window, and then we can view xprop messages here. We deselect node because we found it severity as error and warning. So we can see this assertion fault here, xprop in combo logic. So we can analyze this. Click show to wave. And if you want to double click, you can go into the source window. And you can add the signal to wave window. Here we can see that the Q is reported, it goes to X at 9 nanosecond, and select goes to X. So if we double click on the select, we can go to the driver of it. So B select equals to 1 BX. That's how we can see where this X propagation comes from. And let's see, there's also another video on a different test case. Let's check that as well. So this is on age-triggered demo. So we'll run this design with different X prop mode. So trap mode, it catches the X clock signal that transition to X. So it catches here straight and then it so then we try to run X prop in resolve mode to see how is it different. So it also show error messages now showing Q going to X due to X propagation as well. But in resolve mode, Q is resolved to known value of value of B when reset is 0. Let's see what's the result for Q in pass mode. So pass mode, the value of Q is always X, even though a known value can be determined. Right. Right. We also have labs for this, but before the labs, let's go through a few more example here. Okay. So let's say, for example, this example again, if statement, if not reset, then Q equals to A. If if low reset low, then Q equals to A, else Q will get the value of B. So we consider this following block. We will discuss only resolve mode of X prop, as pass mode is more pessimistic and X is propagated whenever there is pass mode. So resolve mode will merge multiple branches, such as previous value of Q, A, and B will be merged in different combination in this example. So let's say, for example, you guys can have a thought on this as well. So let's say, for example, reset, there's no change, it stays 1. So theoretically, if it stays 1 and clock goes from 0 to 1, it's pause age. So the final value of Q will get the value of B, because always at pause age of clock or negative of reset, it will trigger this block. There's no X prop, this is a normal flop output. But if clock goes to X, so as we seen just now, if clock goes to X, simulator will treat this as a pause age trigger. So this will trigger this, and there's no change of reset. Reset is still 1. So Q will ideally take the value of B, but also the value of previous Q, as it might not change the value of previous Q. And then if clock goes from X to 1, there ideally I don't think there's any difference. So Q will get the value of previous Q or the value of B, because it might trigger this pause age as well. And if clock goes from X to 0, it's a NAS edge, so there's no change here because that didn't trigger this always block. And let's say, for example, here, we have no change on clock, but reset is going from 1 to 0. So what's the final value of Q here? So since reset is going to 0, so it triggered this first if block. So it's A and there's no X prop, it's a normal reset. But if reset is going from 1 to X, so 1 to X can be either staying at 1 or it can either stay at 0. So it can either remain at previous value of Q or it takes A. So X prop in reset. If if reset goes from X to 0, so what will happen if reset goes from X to 0? So it can be either going from 1 to 0 or it stays 0 to 0. So the final value of Q can be either previous value of Q. Oops, sorry. It will go to 0, so it will trigger nav edge even though it's from 0 to 0 or 1 to 0. So Q will ideally take the value of A. And for the rest, it's the same. Any reset that goes to 0, it will only take A. Doesn't matter of the X propagation, because this is resolve mode. It will try to resolve if it can goes to a known value. But for reset to change from X to 1, so X to 1, so it can be either 0 to 1, and there's no change on clock. So since it's either 0 to 1 or 1 to 1, so it would take the value of oh, it will not change this because this always block is a pause age of clock or nav age of reset. So any value change from X reset to 1, it will not change. And then let's see the other one. 1 to X. So reset 1 to X, but clock stays at 1. Clock stays at 1, meaning this block will be triggered. And then reset will go to 1 to either 1 or 0. So the answer is it will merge Q and A. So what happens if it's changing both at the same time, reset to 1 to X and then 0 to X? This will cause a race condition, similar with the below. It will cause a race condition between clock and reset. So On Questasim, we also support for case completeness in terms of case block, where we consider all possible values for the matching of X in the branches. So X0 will be resolved to value A and C. So in this case, X0, let's say this X0. So unknown 0, it will go to A or default C, because 1, it will go to 1. Or X1, it will go to B or C. Or 0x, it will go to either A, B, or C. So 1x, it will definitely go to default. And then we consider another block, another case block. So if select is 0x, Q resolve will go to either A or B. But if the select if X or 0, so it's either this A or C. What happens if it's XX? In this case, all of this will be considered. So we can refer to the lab later on 01 full case with no default. But what happened if we added a default here? Default Q equals to E. Does it change our result? So let's see. So 0 and X, 0x. So 0x should be A and B in the previous slide. But now there's a default. So we include default in the resolve as well. So this is the same. So X0, so A, C, and E. So we can refer to the other lab as well. So one more last block here. What will be the value of X, 0x? Since we have specified 0x here, Questa disable Xprop if any branches have X or Z state, because this is explicitly users and user intention is to handle X. So Xprop is disabled in this case block. All right. So let's take a 15 minutes break, and then we'll come back and start with the labs. Let's take 15 minutes. I'll send the files to you, T. Yeah, thanks for keep helping to send out them.
Okay.
Thank you. Okay, let's resume our lab demonstration now. So I hope everyone have the lab cases from T already and you have it in your environment. So let me share my screen and then I'll walk through the lab case as well. So again, if you guys have any issues running the labs, let me know, and then we can see how do we resolve the issue immediately. Then you can explore around with X propagation. So I've sent two tar files. Let's see. So I have xprop lab and also xprop recap lab. So let's do the recap lab first. Let's see. Recap lab cd recap labs. So every time we have this lab cases, let's check the make file. And for this recap lab, we have also readme file as well. We can open that up. So on the README file, we can see it's instructed for us to make run resolve, and it will return multiple xprop assertion. We can backtrace the X and fix the code from duty or the TB. We can choose any mechanism without impacting the functionality to remove this X issue. So once we have it run clean, then we do it again. We do run resolve again, and we have to make sure that run pass is also clean. So let's see from here. We can see we have a run resolve, and run resolve have a dependent on clean, compile, optimize, and simulation. So let's see each of the following command first. So on the compile command, it's the very straightforward vlog. We just specify system verilog and all of the verilog files. And then on the op resolve. So this is optimization phase. We use vop dash o, and then our output DU name, our top DU, which is TB, and then our xprop mode is to resolve, and we report a warning instead of an error. And then we have dash L resolve.log. We will have our log here deposited here. Okay, let's do it. Let's make run resolve. All right, so let me maximize this. So we can see there's actually a few X propagation and there's a lot of warnings here where it says that Q goes to X due to the propagation. Instead of looking from the terminal, let's check if we have any issues with the VOP. See the log. Okay, VOP log seems to be fine. Yeah, exited without any errors. And then now we look into the vsim log. Okay, vsim. So we can see actually the first X propagation comes here. So it says that Q goes to X due to X propagation, and it happens at time 0 at this file. So the file is mux.ff and at line 67. So let's check the file. Line 67. So it enters X at here because of Q going to X. So in this case, I'm guessing that the select goes to X. We can also open up a visualizer. Let's do that instead. We go to the make file. Let's also check our run.do what's inside. Let's run all and quit. Okay. All right, and then we can open up this design file and also my QWave. Let's see which signal is it complaining about. So it's this scope TB, T1, G1, and Bmux. Bmux. And we look at the variables and a variable Q. So let's add this to wave. Okay, we can see this whole 16-bit is being driven to X. So what we can do here is we can trace the driver, and the driver is coming from here. So select at here, it's X. So we can trace what's driving select. And we can see here, we always begin select is X, and then let's see select. Does it change to anything? Okay, it changes to in, see, begin to case. All right, so let's see. What we can do directly is, I don't think case changes anywhere. Like we can add it to wave. Okay, change to 0 here. So how about our B select? It only changes here. Okay, it only changes here when our state equals to 1. So at 5 nanosecond. So since this is at the initialization state, we can change the runtime. So let's do this. Can do a tickle. In this .do, we can also do it like this, run dash all. Before run dash all, we can do xprop disable. And then we run, let's say for example, 5 nanosecond, and then we enable the xprop again, and we run all. Let's try doing that. So this lab test case is actually very free. You can do it in any way you want so that we can mitigate the X from the design. So we can, from the README, we can do any mechanism that we want without impacting the functionality. So by changing when do we activate the X propagation, that should be fine. And now we see the design and also QA from visualizer again. Okay, now MuxQ is not having any issue here. So let's go to the log file. Sim resolve.log, we reload this. And the first error that we encountered is no longer there. But there's also another error here at line 67. So it's in the same file, line 67 at time 9 nanosecond. So let's see 9 nanosecond what's happening. So we can actually click here, time 9 nanosecond. And the same file, let's see, G1, G1 Bmux, and then line 67. So this select goes to X at 9 nanosecond. It comes back up. And Q doesn't seems to have problem here. Let's see this X at here. So we have X again at 16, at 11 nanosecond. Let's fix this one. Let's see if there's any underlying issue from here. So let's say if I want to see my Q, let's trace again. Where is it coming from? So I have my active driver on. So let's trace this drivers. So it's the select that is coming to HX. So let's trace this. And again, there's a, let's see, always at begin. So this is initial time. It can't be there. So let's see. It's fine for B cell. It's going to 0, going to 1, going to 1. Oh, if there's any changes, then we begin this. So this is very bad coding style. So let's change this as well. If there's any changes in variable, then it goes to 1. So let's change B select. We'll change B select to 0 since it does not implicate any issues. Let's see. So we changed that and we managed to fix the earlier X condition where now the next X condition is only coming from time 23 nanosecond. So on and so on, because this is in a different marks as well. So by fixing all of this, then we can say that this is this lab is already completed. So if you guys have any issues on the lab, and since this is a very lengthy lab, we have also other labs to move on to. If you guys have any issues on this lab, please let me know. Else we'll go through different labs as well. This is a very good lab so that you can practice how to avoid having X in your design and throughout your simulation run. And from here, you can also see a lot of different warnings and different messages that hint you where the X is coming from. Then you can also make use of visualizer if you add only debug and plus design file in VOP, and then you add dash q with db plus signal in your sim resolve. Then you have the necessary information to bring up your visualizer. So let me write it down. To bring up your visualizer, you can easily just use this and design.bin and qwave.db. So from here, you can go and trace back what is causing the X. All right. So let me try another lab. So if you guys have any question with this lab, please directly let me know. Then we can help you to resolve it as well. Let's go to the other lab. So this is the lab we have seen in the presentation session. So let's check on this lab as well. So first thing we do is to gedit run me so we can see what are we running. So we are only running to clean the work directory, and then we vlog for compilation, and then vop to do the optimization. And right now we are doing resolve mode for this case. And then we do vsim and run 100 nanosecond. So let's run this directly. So let's review back what this case is about. We can go back to the slide. So this is the design on the case that we had. So here we can see if our select is 0x, we go to Q resolve of A and B. And then select is X is 0, we'll go to resolve at A and C. And then if it's XX, we go to A, B, C, and D. So we see select is 0, 0. And then the value of Q. So in this same similar case, we can also see in a different pass mode. So let's try pass mode on this one. Oops, sorry. Let's try the other lab with a default here and see how is it different. So we added a default in this O2 lab, so you can check what's actually the difference between running with the default in case statement or without case statement. So this is for you to compare it yourself. So for example, this is without a default, and then we have a default at here. And then on the lab, we use a different select value, for example, 0x or x0, or 1x or x1. So you can see what kind of different results are coming to the output of Q. So just to analyze the dot, we have a lot of set of signals and then select with the output Q. So just like the presentation slide, it is just using this block of code and without the default for the test case 0, 1. And then we set an initial value for each of this signal. So you can see when we set the select to 0, 0, we also set the output to be 0 first, and then we set the select to be 0x at 2 nanos at 2 timestamp. And then you'll see what is the value of the output Q. All right, and then if there's no issue with this, let's move on to the other lab. Let's check on the other lab as well. All right, and then in the other lab test case under demo XProp modes. So this is to demonstrate different XProp modes and the output of the result of the output. So this make file, we include a make trap. So it runs XProp in trap mode and shows the XProp messages reported as warning. Or we can also make resolve where we can run it in resolve mode. Then the XProp messages is also reported as error as we define it in the command line. And then for pass, we can run XProp in pass mode, and then XProp is also reported as error here. So we have a visualizer up as well for the command. Let's try running with pass mode. Pass. So theoretically, since pass mode is X permissive, so the result will be always X unless there's no X propagated in any of the signal. All right. And just for clarity, let me open up the module as well. All right, and then we go to our resolve mode and we can theoretically see the error coming in. So let's see what's our resolve. We do op r. Okay, we have report with severity error, and we run xprop with resolve mode. So here we can see the severity of the error, and then we reports the error as q goes to x due to propagation. And then another one, one more, let's test one more on the trap mode. And because trap mode, we put it report as warning, severity warning, so it will give a warning instead. Okay, so this is the labs for X propagation. We have included everything. This lab is particular on each of the different X propagation modes, and then you can see different outputs from each of these propagation modes. And depending on which kind of scenario that you would prefer in your simulation result, you can choose either resolve, trap, or pass. So ideally, you will do if you want to clean up your simulation design without any of the access as mentioned in the previous slide. So we should do trap mode first to clean up the first X, and then we do resolve mode, and then we do pass mode so that we can ensure that there's no X propagated or any X issues in the simulation design itself. So, yep, that's all for X propagation. Now let's move on to CDC and linting. So if there's any question on X propagation, you can ask now. If if not, then we'll move on to CDC and linting. Let me get out the slide. All right, so let's begin. Since there's no question on X propagation, let's begin on introduction to crystal lint and CDC for designers. So the agenda that we have is only these two big topics here. CDC Cresta Lint, and also Cresta CDC, which is a clock domain crossing verification. So on Cresta Lint, this is our intent. Cresta Lint is intent focused insight to help from creation to completion. So we have three functional pillars. Let me show you. So the first functional pillar is to produce, to prove, and also protect. So to protect the function netlist based on CDC analysis is important, and they have the same common foundation here. So on producing, it's the idea from HDL designer, and then on the initial RTL quality focus, we are proving in terms of Cresta Lint, Cresta Auto Check, Cresta X Check, Cresta CDC, and Cresta RDC. This is the whole development process, but it is also on the same common foundation where you can easily transition between this analysis and beyond. So once you have all of this done, then we go through Cresta sign-off CDC as well. So as I mentioned, it is designed for consistent throughout the entire flow, where we have this shared attribute throughout all of the different checkings, such as Cresta Lint, Auto Check, Cresta X Check, CDC, RDC, and Sign Off CDC. So all of these attributes are shared commonly, and we have consistent compiler and foundation. So debug and user interface are shared among all of these as well. So directive approach, constraint methodology, and the status flow are all shared between all of this. So you can sign off all of it on the same foundation without having to change a lot in terms of the flow. So what's the benefit from having this common foundation is that can have a fast bring up of all tools. We don't need a long curve of learning. We can just use a short learning curve for debug. We don't have to learn individually for each of these tools. So now we go into the proper lean checking, auto check, and also X check. This is for early intent insight. So let's say this is focused on the proof pillar, where we do exhaustive analysis early in the stage to mitigate actually a lot of future issues. So this exhaustive analysis includes this synthetic, semantic, stylist, and structural issues. So all of these checks are checking whether the first one is to check whether the code is properly constructed. And in terms of schematic, do the elements make conceptual sense? Or the stylistic, is the code properly named or commented and laid out to meet the requirements? And in terms of structural, do the pieces form a coherent whole? While Questa Auto Check checks for sequential, are the states and sequences well performed? And as we mentioned just now on the X propagation, Questa X Check, we are to check whether all of the items defined where they needed and will the design behave consistently. And then these three RTL analysis tool, let's say for example, Lint, AutoCheck, and S-Check, it actually intent focus insight for designers where we provide verification automation, improve functional verification efficiency, and it use team agility. So what we can say is that if we add Lint, it's like adding at least one engineer to every of the project. Because Lint is already a very hassle work where you check all of the languages. And using all this tool, we can find issues actually very early to reduce the cost to fix. And designers is fixing issues early, improve downstream verification as well. So how does Questalin help you? So Questalin provides adaptive integrated insight to engineers so that we ensure that the quality and intent are met. The adaptive is to ensure that change only reporting and it results in correlation. So this ensures fastest possible closure. And to accelerate test cycle fix, Lint uses identical status flow to CDC. And also Lint use pre-verified compiled FPGA libs. It provides insight into the design quality scoring, and it is also collaborative team-based issue closure so that you can help the managers to track the issue and close everything efficiently. So all of these are intended to help designer to focus on, to understand where to focus on for the maximum ROI. And Lean actually comes pre-configured methodologies such as for the IP, SOC, and FPGA's development with a standard list of goals here. So all of these individual goals, they actually have a specific check set to itself. And we also have a different additional check set, which is standards to goals on Stark. So this Stark is actually more of a instruction set and it is designed for immediate intuitive feedback on design issue. So this save a lot of time and effort, making development process much more smoother and efficient for everyone. So additionally, it is possible also for teams to customize all of these goals and checks to meet the specific requirements for each of the design. So linting example where it can identify, for example, as I mentioned, the pillars just now, style list, schematic, structural designs issue, even before the simulation start. So to make you understand how does linting work, it is actually a static analysis where it is fast and requires no input apart from the RTL code itself. So if you have RTL code, you can already do lint checking. And lint checking will provide a UI in in our debugger visualizer as well. So on structural issue, we can see if there's any combinational loop or reset that are being used as data, or any undriven input or outputs that are unconnected. So this we can directly check from Lint itself without having it to show as an error or warning downline in the simulation. So for schematic issue, we can check whether there is unsynthesizable code or any simulation or between simulation and synthesis mismatch, improper assignment, any width mismatches, or any date or unreachable FSM states, latch interference, and inconsistent clock and reset style, or any date code that are very unnecessary. So in terms of stylistic issue, there's also adequate commenting. So the naming convention and also unused object and the maintainability. So the workflow is fairly straightforward because what you need is only required the RTL at each state and it is being analyzed by Questalint. So this, once we use Questalint, it generates a report that can be that the user can use to view in the debugger. And then from here, any status flow or directive are fed back into Questalint and then executed anytime as necessary. So Questa Lint comes in a number of pre-built methodology. So we have the FPGA methodology, IP methodology, and also SOC methodology. So all of these pre-built methodology have very similar structures to them where we begin from start, and then there's a simulation in between, and then there's a release. But it gets more complicated as the design gets bigger. From IP, we have also the implementation stage, and SOC methodology, we have a start planning simulation implementation, then only release. So it depends on what type of project that you are doing. You can use a Lint pre-built methodology to release it for further simulation process already. And this is one of the things that makes Crystal Lint unique to itself. It's called Crystal Lint Quality Score. So it helps to analyze the result of your analysis, and then it applies scores to your analysis and then categorize them according to what Crystal Lint thinks. So this helps you to understand the risk, and you can make decision based on the scores throughout the design. So the scores are further a check that ensures all input signals, such as underscore I, are naming or nomenclature style. So this is categorized as also known as naming style. And RTL design style check is basically just your code structural check. And simulation check is to check whether there's any underlying issues that may affect the simulation, such as if there's any extra combo loops or any dead combo loops. For implementation, this is to check related to synthesis check. So it compares whether if it has any mismatch between synthesis to RTL gate level. Then RTL Lean's quality score actually answers these questions. Which part of your design should you address first? And then which block require the most work to clean up? And is there any important blocks that does not meet my quality requirements? Or which team or contractors produce the cleanest code? So this helps designers to answer all these questions at one go. Then in addition, Cursor Lean also can be used to compare previous run. So for example, if you have a reference run that you ran last Friday, so you can compare the lint result from the design today and the design from last Friday. So it will also run calculate the percentage of your score comparison between the latest run and the previous run. So you can compare what is it the difference between the code that has an effect to the scoring. So you may have a new errors introduced in the latest design, but this error was not seen in the previous design. And this comparison can be made either in batch mode or the GUI mode. So this is the summary on why we think Questa Lint is very competitive in the market. So the features that should be common in all linting tool is out of the box methodology, goals, and also the standard supports for quick result. Then it is design quality scoring to indicate what needs attention first, customizable goals and configurable checks to adopt to the target design. So let's say if your design is somewhere in between IP level and also SOC level, but you don't want the complexity of SOC, you can actually configure your checks and also customize the goals to meet your design target. And then it is intuitive check names for easy understanding of the results. We can change only reporting to focus analysis on what is changed recently. And there's also schematic cross probing to accelerate debug. And it is very audit focused, flow and report generation to demonstrate standard compliance. Right? So more on the summary itself. So Lint is actually a mature tool which is available on Linux and Windows, where it is unique, where Lint provides new capabilities in linting. So in Lint, we have Lint Assist. So this is machine learning based data analysis that collates issues to provide prioritized and actionable results. And it is also collaborative debug, where it is a team-based issue closure environment to clean the design very fast. It has a modern architecture supporting for the latest language features and the largest design you have. So in terms of maturity, Lint is also integrated with Questa design solutions and beyond. So you can compile once and it is already done, where we'll have minimal surprise later with common compilers with all Questa products. And you can learn it for once and it will have a minimal debug learning curve with a common debug interface based on visualizer. So if you already know how to use visualizer, you can also use lint on visualizer for a very common debug interface. We can also close analysis quickly. Common status flow and constraint methodologies are familiar. It is very portable throughout the tools. Right, now we go into CDC already. So on CDC side, single model clock designs are long gone already. So current design, we make use of a lot of multiple clocks in our design. So let's take a daily example. For example, our smartphone. So for a simple question is, how many different clock domains do you think are in our smartphone? If I were to list down on top of my head, I can think of a CPU, GPU, a port C, Bluetooth, the display. But these are the only easy ones that I can think out of my head. So, but the point is that there are many asynchronous clock domains within any given design, and across in between that must be handled. So any crosses between asynchronous clock, we must handle it uh, properly, unless otherwise there will be a lot of issues on later on in the simulation stage. So since we know there's a lot of issues between clock domain crossing, but how did all of the previous method deal with it? So initially, many will fall back to trial and error in both simulation and static analysis. This trial and error is a very wonderful tool, a very effective way to doing it, but its effectiveness is only contained within an individual clock domain. So what do we know about the problem with cross-domain crossing signals? So cross-domain crossing signals have a complexity that is unique to them compared to any single clock domain signals. So this asynchronous clock have unpredictable phase with respect to other clocks. So a CDC signal must travel across asynchronous clock domains. So for example, here we have clock domain A, and then we have a clock domain B. We have a transmitting signal to clock domain B and receiving from this side. So this is what we call as clock domain crossing signal. So we'll discuss further on what will this cause, but so even though we know there's a transition between this and there will be a violation between a setup and hold time. So how do we avoid this? So this is actually impossible to avoid, but we can try to deal with it and minimize the damage done. To deal with it, we actually use synchronization logic. So every logic designer will also tell you that if you violate the hold or setup violation, you will introduce metastability. So what is metastability, right? So metastability is a phenomenon that occurs if any hold time or set time is violated, and then you have your output to have a very long time to decide whether it will settle down on 0 or 1. So basically, because of the data and clock, so for example, this graph here, data and clock are changing in very close proximity to each other. The resulted output of this will not be able to know whether it is changing or is it not changing. Within a normal timing parameter of a flip-flop, it will not know. So ultimately the output will change to either 1 or 0, but in many, many cycles beyond this. So hence, this will cause the output to be not predictable, and we cannot model it by digital simulator. Why don't we take a closer look here? So when we put Q on oscilloscope, for example, this snippet here. So this is what actually metastability looks like. So the signal Q have metastability at this certain point, and it does not know whether to settle down on 0 or 1, but it will also eventually settle down at some time frame later. So look at how unpredictable this signal is and how far down the clock cycle before it settles down. So this is an example of what occurs in metastability that happens due to set time and hold time violation. So let's say setup violation. For setup violation, you can see the data age just rises just before this clock age rises. So the output Q, as you can see from the previous slide on the oscilloscope, the output Q will take some time to decide on settle down on whether 1 or 0. And it may take a while up to a full cycle delay. So similarly for a hold violation, you can see that this data D rises very close proximity to the clock rises. And we can see metastability actually have a different effect between both of them. So for setup violation, so simulation captures a 1, while silicon can produce either 1 or 0. But in hold violation, simulation captures a 0, while silicon can produce either 1 or 0. And this result in, for setup violation, a possible single cycle delay effect in silicon versus simulation. But for hold violation, it is possible that it bleeds through the effect in silicon versus simulation. So what we can understand right now is that when we have clock domain crossing in our design, we cannot fully trust the result from our simulation to reflect how silicon behave, because there is clearly a mismatch between simulation and silicon. So designer, of course, they know about this metastability, and we know that we cannot avoid it, but we can try to reduce the effect. So that's why we use synchronizers to confine the metastability signals. So although we use synchronizers and we can confine it within the synchronizer itself, but metastability still happens inside the synchronized structures such as this dual flip-flop synchro. And there is actually a delay throughout the synchronizer which become randoms later on. So let's say, for example, let's take a look at the setup violation. So there's a transition between input synchronizer, which will propagate to the output between 2 and 3 active edges of RX clock. That is because we have to go through at least 2 flip-flop, and there's a delay of 2 to 3 active edges of RX clock in the silicon. But in terms of hole violation, so transition at input synchronizer will propagate to output between 1 and 2 active edges of RX clock. So what we can learn from here is that, let me just share this. So if you can see from this metastability window, so TX here is violating a setup violation. So TX is going up high at time of 1 of I. And then TX goes to 1 just before this I. So the second flop will only catch it at I plus 1. So the Rx will only toggle at the time I plus 2 because of the delay between the flip-flop. However, if metastability happens, the second flop may not capture 1 and still see 0. So this, if metastability happens inside this D flip-flop, and because of it takes maybe 1 or more unit cycle before it settle down, so it actually propagates it to I plus 2, only the Rx is changing. So if this happens, Rx only changes during I plus 2, and then it will settle down to 1 at I plus 3. So however, if uh, metastability happens, then second flop also will capture uh, 1 at I plus 1. So now we know about synchronizer. So we can ask ourselves whether we can just add this dual flip-flop synchronizer and be done with this metastability and also the CDC issues. Simple answer is no, we cannot just rely on dual flop synchronizer because dual flop is only helpful in certain situations. So what if, so for example, what if we have 256 data bus? Then we'll have to add up to 512 flops to our design, which is not a very viable solution. And so this is where transfer protocols come in. So in order to handle large data bus, we need to insert 2-to-1 mux. So for example, this one, 2-to-1 mux to handle the data, and we add a valid signal to the dual flip-flop. So this valid signal will tell the receiver domain that the data is stable and ready to receive from the transmitting domain. Then of course, the protocol must also be verified. If it's not verified and the protocol is violated, then the data can be lost. Simulation may not show a failure, or silicon implementation will eventually fail. So one of the major issue with large data buses are proper handling of inserted between transfer and receiving domain. So if the logic in domain B depends on such timing relationship, it will lead to a functional bug because of unpredicted delays through synchronizers. So we learned that using synchronizers, there will be delays that it might be hard to model it in simulation. So in this case, this bug can be a reconvergence bug. And this is what happens if you have multiple parallel signal and the bits are captured in different cycle. All right. And then next on comprehensive solution, it's 3:50 right now. Why don't we take a short break for 15 minutes and then we'll continue finishing this Questa CTC. It will take a short break before we continue forward.